we've had a number of use cases where older assets, it's been a big barrier in going digital because the information is stranded, if you like, on paper. And so we wondered if there was a way we could use machine learning to identify particularly instruments on P and IDs because they are not straightforward because of their shape. Could we use some image recognition to extract the instrumentation of P and IDs and very quickly then build something like a knowledge graph? So take it away, Andrew.
Yep. So I'll probably be fairly briefly going through the slides I did for a talk in Aberdeen for a conference not 2 weeks ago. As Murray said, a lot of this is to do with digitalizing data in the most effective way possible. And in our case, it was digitalizing P and IDs, which can be a tricky thing in regular code, but utilizing machine learning allows us to more rapidly produce accurate results. I'll quickly show you a demonstration of this working so you can get a better idea of the context when I go in to explain it. So here we'll be grabbing a PNG for this first one of a snippet of a P and ID. As you can see, we're uploading it. And there it is previewed. So what this is for context is it's a streamlit front end for prototyping. We basically allowed us to deploy it and make it easier instead of looking at a lot of code. So here it'll be running. We have cut this down a bit, but it still takes a while. As you can see there, we have all the instruments detected with a few false positives, which will be in the middle of those circles. We can save the detection now, which will pop out a list of reference images to the cropped instruments on the P and ID. The second half of this will be the OCR, the optical character recognition, which will basically be looking through the instruments and seeing their text, which could be sometimes quite rough, even on the human eye. So we've designed a machine learning that can look at it and make the best judgment case for what that writing could be. And then it'll process all of that information into a CSV file. That there's the naming convention builder. So obviously these will be tailored to different companies and how the code for their tag systems works. So we'll give it a second. I swear it takes longer every demonstration.
Yeah, but this is real time. This is no
Yeah.
sequences have been shortened.
So there we go. We have a fully, well, an almost fully complete CSV ready to download with the tag name, class, system, function code, and loop sequence, and a reference to the image. So briefly how we did it, we used the Yolo V5 object detection algorithm, which is through our comparisons that we found ourselves is very fast and optimized for what we needed it to do. The likes of Tesla use it for their cars and their object detection systems around their cars, so it's quite renowned. And this allows us to make less data ourselves because we'll be using this to basically take us all the way there, and then we'll tailor it ourselves on the top to our specific use case. We still did need quite a lot of data. I think, self-annotated about 1,200 snippets of P and IDs, circling boxes around the instruments and stuff. And then on top of that, we augmented it in different ways to add to our raw data pool. This will all help with accuracy. We also did training and model fine-tuning, which took quite a lot of trial and error. You can see some of our values on the right side. I won't get too into it, but it did take a while to get it just right, fine-tuning stuff so we could get a good balance between what it could detect. The second half of it was the OCR, as I mentioned, the optical character recognition. So this is where we were taking, as you can see, the image on the right, some more rough looking values or instrument names, and using computer learning to train through data like you see on the left and be able to see this and interpret and extract it out and then put it into more clean computerized code. And then finally, the naming convention. We wanted to make sure that for our clients, it was very easy for them to immediately be able to customize their responses. As you saw, there was the drop downs. which allows you to quickly insert and tell the model exactly how you want the pattern to come out as, and it will go through that and do it for you. So we'll just quickly go through the longer version of this. I'll show some of the parameters. Once again, we're loading in a model. You can change the models. So if there's slight differences in P and IDs, we can train and set up a different model for you. This time we're using a full PDF P and ID. And then here we have two sliders. As you can see, we have a confidence threshold and a grid size. So the grid size one, as you can see in this preview, is for breaking up the P and ID. This is especially needed for when there's more instruments and they're more clustered. It'll help the machine learning system break it up and process section by section for more accuracy overall. So as you can see, I've changed it from 6x6 to 8x8, which will take a second to run. And in doing that, it's not necessarily relevant for this one. As you can see, there's not too many instruments on the P and ID. But for other use cases with the bigger clusters, it's more important. There is also an overlap because obviously there'll be some instruments that lie on the grid lines and we'll need it to either drop one way or the other and not just get split in half. Confidence threshold, if you know about machine learning, is basically when a object is detected, the machine will have a 0 to 100 of how confident it is that. 0 being it's very confident it's not that. 100 being it's perfectly confident it is that. But usually it'll lie somewhere in the middle. This will come with like false positives where it maybe thinks it's something, but it's not necessarily. So we can adjust that slider of that threshold so it knows when to bring in a detection and ignore a detection. For our case, we keep it quite low because we want to make sure we get every instrument, and a few false positives are fine because we can cut some out. As you can see here, we've detected, I think, 98% of this P and ID with all the boxes annotated. And we will now crop the images with another slider because sometimes the instrument names may lay outside of the instrument. So you want to make sure the box around it can be adjusted to not miss any of the writing. So there we have our cropped images now referenced below. And we'll move over again to the OCR. So here we have another trained model with the Yolo, specifically for this OCR work. We'll change our naming conventions. So we'll have a system number. You can change if you want to have hyphens or spaces with loop sequence. You can give hints to the machine. And this is all just early prototyping for what we would see, creating this more dynamic system to help the users get through it and get exactly what they want out of it. The extracting time will be slightly longer or not, depending on how many instruments are present. And then, as you can see here, we have it. The downloadable CSV. We have other we have other parts in this just for debugging and to show off that we are able to capture text even outside of the instruments themselves on the P and ID, which may be relevant to you and you want to be processed.